Hello, everyone. I'm Adarsh. I work in one of Simon Conscious groups in Durham, where we've built a microscope for ultracold RbCs molecules, and I'm going to talk to you a bit about that today. So, to start off, well, I'm not going to say much about the motivation for working with molecules, especially to this crowd. Just that well, they have a nice long-range tunable dipole interaction, which we can use. What makes it an interesting tool for um, realizing some many body systems and quantum simulation. I guess as the ultracold molecule experiments around the world typically fall into two categories. You've got experiments with bulk gases. So a good example is the experiments we've all heard about today. In these experiments, the imaging is typically done with absorption imaging. So for associated molecules, you usually split them apart and then image the atoms from that, or you have tweezer experiments where you can image, well, you load individual molecules into your optical tweezers and you can image the molecules in the tweezers. We saw some nice results from, I think, Lawrence yesterday. One sort of nice thing about rubidium cesium is that both rubidium and cesium have sort of been, investigated thoroughly in atomic physics. So it's pretty much a solved problem to image both of them on their own. So when you work with rubidium cesium molecules, it's quite easy to split apart your molecule and then image both the rubidium atom and the cesium atom from the same molecule, which gives you 2 bits of information from the same molecule, which is something we'll, guess, use, as I will talk about in a few slides. So it would be quite nice to, I guess, use have this single molecular resolved imaging in bulk gases. So rather than image the, ones of, or ones or tens of molecules you see in tweezer systems, typically with molecules, to image the thousands of molecules you see in bulk gas experiments and in dipole traps and lattices. So with ultracold atoms, this is already kind of a solved problem, I guess. You've got the advent of quantum gas microscopes, so it's been sort of maybe a staple of atomic physics for the last 15, 16 years, ever since the first microscopes in the, I guess, top 2 papers for rubidium. In the many years since, there have been, I think, quite a few microscopes developed around the world with many atomic species, including cesium. So in some way, it's, well, the microscopy in atomic systems already been developed, and it's quite nice to generalize this to a molecule system, because when you have molecules trapped in a lattice, the lattice spacings are typically submicron, which is closer than you can get usually with your tweezers, which means your dipole interactions are quite strong. So in fact, this has been previously done in the Princeton group in Wasim Bakar's group, where they have sodium rubidium molecules and they load in a lattice and do microscopy by separating the molecules and imaging the rubidium. And they've, well, with their lattice reconstruction, they've managed to see correlations and there's a fun thing with, depending on how far apart your molecules are, you can see the different correlations. So we want to do something similar for rubidium cesium. So in some sense, there's 2 bits to the experiment. There's the single site imaging, which you have from the typical microscope experiments, and you want to make molecules. So for the single site imaging, we trap. So we first did all of this with atoms, so both cesium and rubidium. So we trap the atoms in a bow tie lattice made of 1064 light, where the lattice sites are 752 nanometers apart. And we use a 7-micron waist light sheet to give us vertical confinement and compress everything into one layer for imaging. And then we can use molasses imaging. So this is a sparse cesium image. So we just use optical molasses, image it with a high NA objective, and then from that we can reconstruct the lattice and the occupancy and find where the single atoms are. And sort of the other side of the coin is the making our ultracold molecules of rubidium cesium. So we have a dual chamber design, so it's a bit of a long process to get everything made, but in a nutshell, we sequentially load and transport rubidium and then cesium into the science cell and trap them in spatially separate optical dipole traps, after which we evaporate down to a phase space density of about 0.1, merge the traps and associate with the usual freshback association followed by stirrup. Quick aside here, we've managed to use some optical feed forward to get stirrup to be quite efficient by removing the phase noise. I'm not going to talk about it at all today, but feel free to check out the paper or ask me about it some point later. Anyway, so now that we have both, well, now that we've got both bits of this initial stuff set up, we've combined them and try and get single molecule resolved imaging in our lattice. So the first step is we make our molecules and then load them into the light sheet and confine them there. So we have about 1,500 molecules of rubidium cesium, and I think for the last 10 years, Simon's been subject to looking at images like that one, absorption images. And then we turn on our bow tie lattice to pin the molecules to their sites, after which we reverse the stirrup and the freshback association, and we're left with an atom pair of one rubidium atom and one cesium atom on every site where a molecule was. From then we use a just optical blast beam to remove one species, because if you try to do some molasses imaging with a rubidium and a cesium atom on, you'll lose both to light-assisted collisions. And yep, so we can choose to remove either rubidium or cesium, and this is what it looks like, which is, I think we can all agree, much prettier than this. So on top is a image of a sequence of about 1,500 molecules where we dissociated and then removed rubidium and imaged cesium. The bottom's the other way around, where we dissociated and then removed cesium and imaged rubidium. So I will point out that we're not doing this from a quantum gas or a DC or anything, so it's quite analogous to the continuum microscopes that Martin talked a bit about yesterday. So now that we have this really powerful tool, we've, I guess, started to play with it. So maybe what have we done? Well, one thing is, typically with the sort of really blurry images, it's difficult to get any measurement of your column density or well, any sort of internal structure. Like we've seen some very good results on that earlier today and yesterday, but I guess we have quite a bit of resolution here. So we take a typical microscope image is shown here. We can take multiple of these to build up statistics, and we can average it out to get a averaged occupancy. I should point out that the average occupancy we see from taking multiple images does need to be corrected, because there's nothing that stops us loading multiple molecules onto a single lattice site, but we can sort of calibrate this out with, just assuming Pesonian statistics. So we just, assume pairwise loss and scale it up. So that's shown over there. And then we can do some loss measurements. So the, I guess, red curve here shows this typical loss measurement. So over here we've trapped rubidium cesium molecules in the light sheet for different amounts of time before turning on the pinning lattice and imaging them. I think just to point out how powerful this is, if you see this point here, that's about, maybe 300-400 molecules. That's all the way over here on this plot, and the y-axis is a log scale. So when we get all the way down here, we're imaging decay quite well with, 10 to 20 molecules in some sense, which makes this a very, I guess, interesting platform to investigate, well, to like prepare impurity states and put them in a bath of a different other state and investigate their collisional properties. So the, I guess, first measurements we've done of just the rubidium-cesium loss rate is consistent with previous measurements of the same in our group. The next fun thing we've done is, so like I said earlier, with rubidium-cesium, it's quite easy to image both rubidium and cesium in the microscope. So we've just realized this proposal made by Covey in the paper 7 years ago, where we map different rotational states to different species to be imaged. So we map our n=1 state to cesium and n=0 to rubidium. So the sequence to do that is, well, the whole sequence is predicated on the state specificity of stirrup. So if you create a mixture of molecules in n=0 and n=1, and then stir up them back to the Feshbach molecules, only your n=0 molecules are gonna head back, while your n=1 molecules are just stay the same. So we I guess how the sequence works is we prepare a mixture of n=0 and n=1 with a microwave pulse. Then we dissociate the n=0 to form an atom pair. At that point, we do a pi pulse to turn the n=1 molecules down to n=0. We then blast the cesium atoms from the n=0 molecules and ARP the remaining rubidium to the 2,2 state. We then go and dissociate the molecule that was in n=1 and is now in n=0. We ARP the rubidium to 2,2, which changes the rubidium in this state to 1,1. Then we blast this rubidium out, and we're left with a cesium atom where the n=1 is, and a rubidium atom where the n=0 was. So we've then done, I guess, the maybe simplest measurement and taken a Rabi flop. So we, at every point on this, we take 3 fluorescence images. The first one is where we image only rubidium fluorescence. The second one, we image only cesium fluorescence. And the third one, we image both. And using these 3 images, we can reconstruct the lattice with the filling and sort of we know where all the molecules were and where the n=1 and n=0 molecules were. The, I guess, final thing we've done that I'm going to talk about is some spatial addressing. So we put in a 817 nanometer addressing beam to just light shift the transition of a small section of our molecular cloud. And then if we apply a pi pulse, if we apply a microwave pi pulse, everything around it gets transferred to n=1, while the light shifted section stays in n=0. And using the similar method to before, we can take an image, and I don't know, we've been calling it the quantum hole punch. You can see a nice circle of the n=0 contained in the n=1 larger cloud. So this, well, if we, maybe make a more complicated system with a DMD, it's going to be quite useful for initializing our system into some disordered out of equilibrium states. Sorry. And I guess the final things are, we've just confirmed that we are in fact pinned by basically preparing a small section like this, blasting out the rest, and looking at the waste with respect to time. The radius of the cloud with respect to time. And when we're pinned over here, it doesn't expand. And we can also do temperature measurements quite well with this, because we can, prepare small clouds and then just let them expand. So we've measured the temperature of our molecules in this to be about 5 microkelvin. So then just quickly to talk about what next. So currently we use 1064 nanometer traps for everything, and we don't have great coherence times here. So the next stage is to replace all of these with a magic wavelength trap, which Dan's going to talk about in a half an hour. And we also want to create colder molecular samples and have denser samples. And the idea for that is we're going to put in a species-specific lattice to be able to separate rubidium and cesium vertically and then merge modulators of them to create our molecules. Well, finally, just want to thank everyone in the lab. So Simon, Phil, Jonathan, Ben, Francesca, and Chris. And if you're interested, I guess, looking at the Cornish group page and the paper that we have on the archive about this, I've made some microscope-themed QR codes, which is a sign of my initiative and not a sign that I have too much free time if you're talking to Simon. But yeah, thanks. And
really exciting images. Let's take one question before we go to the break. Yeah.
Yeah, thanks for the super interesting talk. I'm wondering, would it be conceivable to image the molecules and then put them back together to kind of initialize some kind of many-body experiment with a known molecule position?
Well, I guess currently we use D2 molasses to image, so the molecules are probably too hot to put them back together easily. But maybe if we, I'm thinking maybe if we use, say, Raman sideband cooling, which has been done in a few other microscopes, that could be a possibility.
Thank you.
Yeah. Let's thank all of the speakers of the session.